Next, we move on to correlation learning rule. Now, in correlation learning rule, the learning signal R is nothing but the desired response D of I. Previously, we would take the difference between the desired response and the actual response di minus oi. But here, the actual response is not at all taken into consideration. Only the desired response is taken into consideration. So the learning signal is directly R is equal to D of I. So the adjustment of the weight vector delta Wi is nothing but we know that it is made up of C learning constant R and the input weight vector. So it is C D of Di and X. Now this rule states that if D of I is the desired response due to X of J. Now here I have specified small x of J because this is a vector. So this is a vector which will be made up of say x1, x2, x3. So many inputs are there. So corresponding to a particular input, if at all the desired response is D of I, then the corresponding weight increase is proportional to their product. So D of I and X, the product of D of I into X. So if at all individual weight vector, if at all we see for input x1, that will be corresponding to xi and di. For input, the weight for input x2, that is wi2, that one would be di into x2, that is the second value in the input vector, and so on and so forth. Now this rule applies to recording data in memory networks with binary response neurons. It can be interpreted as a special case of Hebbian rule. In Hebbian learning rule, we consider R is equal to OI, that is the expected output. So rather than taking the expected output, we are taking the desired output. But desired output will be indicated in the form of +1 or -1 or 0 or 1. That is only binary activation function. See, Hebbian learning rule can be used for binary as well as continuous. Any activation function can be used. But here it is a special case when a binary activation function is used, and for OI is equal to DI. So this D in place of OI here we are replacing with DI. So it can be considered as a special case. I'm not saying that it is a special case. Now, the difference between Hebbian learning rule and correlation learning rule. In Hebbian learning rule here, R is equal to OI. So OI is the actual output, and the desired output is not at all taken into consideration. So it is unsupervised learning. Whereas correlation learning, we are directly taking the desired response into consideration and not the actual. So it is a supervised learning rule. Now, like the Hebbian learning rule, correlation learning rule also requires weight initialization around 0. So the initial weight should be selected very close to 0. Now we move on to the summary of learning rules and certain of their properties. Now we have seen the first rule which we have seen is Hebbian learning rule. So in Hebbian learning rule, first we shall see the weight update. We have already seen it. It is C, that is learning constant, actual output into the input vector X. So initial weights are close to 0. It is an unsupervised learning rule, and any type of neuron, either bipolar or unipolar binary neuron or continuous sigmoidal functions, unipolar as well as bipolar, can be used for this Hebbian learning rule. Moving on to perceptron learning rule, here we are taking the R signal, learning signal is Di minus Oi. So desired as well as actual outputs are taken into consideration. Initial values of the weights can be anything. It is a supervised learning rule. Why it is a supervised learning rule? Because D of I is present. So if at all you see here in these 4 learning rules, D of I is present in perceptron, delta, Widerhoff and correlation learning rule, D of I is present. So all these are supervised learning rules. Whereas in first one, Hebbian learning rule, D of I is not present, desired response is not there, it is unsupervised learning rule. Now, perceptron learning rule, I have told you it can be only used for a discrete neuron, which is perceptron. So, either bipolar or unipolar binary discrete neuron can be used. Delta learning rule is only used for continuous activation function and not discrete. And that is the reason there is an extra term here, fnet dash, that is the derivative of the activation function which will be included here. In Widerhoff learning rule, rather than mentioning OI, we are mentioning directly net of I. So that is what is the change in Widerhoff learning rule. Rest everything. Again, in Widerhoff learning rule, any neuron characteristics can be considered because actually the function is not taken into consideration only here. And correlation learning rule, again, it is C d of I, sorry, di into x, and it is required that the initial weights are close to 0, and any neuron characteristics can be used for correlation learning rule. Now there are two more learning rules which we have to consider, that is winner-take-all learning rule, which is also called as in-star learning rule, and then we have out-star learning rule. So this we shall be having a look at in the next video.